Hello everyone, we are from Group F and we're going to present this journal called The Next Generation Power Electronics for Electric Vehicles, the Role of Wide Bandgap Semiconductors. Here is our contents, and here's our team members. So we have Fatih Filbert Farudin, me, Mila Abimanga Hendrickson, we have Kevin Pradipta, Alina Sharif Agustian, and Sylvia Nasra Zahira. Next.
So I'll start with the introduction. My name is Fatih Robert Farudin. So this actually in recent years, we have moved from nine alternatives to central figures in rural side of sustainable transportation. And then at the end, as vehicles become more electrified and compact, the need for efficient, compact, high temperature tolerant, and high frequency device has become a major engineering concern. Next. So the fundamental of wide bandgap semiconductors. Next. So actually, the band gap is a core concept used to describe the electrical behavior of a material. It is defined as the energy difference between the valence band, which contains bound electrons, and the conduction band, where all electrons are free to move under an electric field. This band gap determines a material's conductivity. So the conductors have overlapping bands. Insulator have a large band gap. Semiconductor like silicon carbide, and gallium nitride have moderate to wide band gaps that allows control over their conductivity. Next. So if the wider band gaps means the more energy required to excite an electron into the conduction band. So it means that the wide band gap material are more resilient to high voltages, less prone to leakage current, and capable of operating at higher temperatures. So this translates to faster switching, greater efficiency, smaller components, and improved thermal performance. Next. So why do we use wide band gap? Physical and electronic advantage. Wide band gap semiconductors offer a set of physical and electronic benefit that outperforms conventional Si-based device. So here's the table that compares Si, silicon carbide, and gallium nitride. Next. This is the continuation of the previous table. Next. So what are the advantage of using WBG materials? So it actually has higher breakdown voltage, higher switching frequency, better thermal stability, lower switching and conduction losses, and higher power density. Next. So for silicon carbide, they are the material characteristic. Si is a compound semiconductor made of silicon carbon. So most common form used in electronics is 4H SiC, because it's has high electromobility and wide bandgap. The structure it's hexagonal lattice with high thermal stability. So and it's produced via sublimation at higher temperature. So the key properties: it has high breakdown voltage, external thermal conductivity, and stable operation at very high temperatures. Next. The application, it's used for traction inverters, DC-DC converters, and onboard chargers. But there are some challenges in using the SiC, because SiC is actually 5 to 10 times higher than, because SiC is actually 5 to 10 times more expensive than silicon, and the density and wafer scalability remain production challenges. Next. And this is for gallium nitride. Gallium nitride is a 3 to 5 compound semiconductor known for its ultra-fast switching and high electron mobility, usually grown on substrates like silicon. And the crystal structure, it's actually word-side hexagonal structure and thin film deposition using metal organic chemical vapor deposition. The key properties: high switching, high electron mobility, and ideal for less than 600 volt application. Next. The application in EVs, onboard chargers, DC-DC converters, fast EV chargers. The challenges for this GaN require thermal conductivity, requires advanced packaging and thermal design, substrate mismatch, and cause lattice defects, and affecting reliability. Next. So this is for compare silicon carbide and gallium nitride. Next. So that's for me. That is for me. And the next slides will be continued by Milo.
Okay, thank you, Fatih. Now, I am Milo Abimanga Hendrickson, and I'm going to explain about comparative material semiconductors. So here is a brief history. So first of all, EV power electronics performance depends on the semiconductor devices such as MOSFET and IGBT. So silicon has been the standard due to its major fabrication and low cost. Thus, the limitations of silicon include the low voltage tolerance, thermal performance, a slow switching speed, and a power density for next-gen EV demands. So the solution by the researchers is actually making a wide bandgap semiconductor such as silicon carbide and gallium nitride. Thus, these wide bandgap devices will enable significant improvements such as the induction inverters, DC-DC converters, and onboard chargers. Here is the table of conversion table for the material properties. So we move on to the bandgap energy. It is the net energy required to move an electron from the valence band to conduction band. As you see here, the highest bandgap energy is contained by the wide bandgap semiconductors. So these wide bandgap semiconductors is ideal for demanding EV applications, including induction inverters and high-speed charging systems. And also we continue the breakdown of electric field strength. It is the maximum electric field a material can withstand before the electric breakdown occurs. And as you see here, both silicon carbide and gallium nitride can block 10 times higher voltages because they have a really high breakdown electric field. This minimizes the parasitics and reduce overall system cost and volume. Next, we turn to the electron mobility. So this actually measures how quickly electrons move through a material under electric field. And as you see here, the gallium nitride have the very high mobility, around 2000 centimeters square volts per second. And it's really ideal for fast switching in onboard chargers, power conversion, and high frequency resonant converters. And then we continue the thermal conductivity, which is the ability of material to conduct and dissipate heat. Thus, it is crucial for reliability and for performance under the load. As you see here, the silicon carbide has the most excellent thermal conductivity. Thus, it is really useful for traction inverters, battery systems that operate under extreme loads and temperatures. While gallium nitride also requires careful thermal management. Next, we continue the saturation velocity. This is the maximum speed electrons can reach in a semiconductor under a high electric field. So as you see here, the gallium nitride has the highest saturation velocity. This high saturation velocity enhances switching speed, reducing the losses in switching and conduction, and also enables smaller magnetic components in converters. And also, we have here the maximum junction temperature, which is the highest temperature at which a semiconductor can operate reliably. So as you see here, the silicon carbide has the highest junction temperature. So the high junction temperature allows devices to operate without heavy cooling systems, and it improves the thermal headroom and especially the power density. Here we have the switching frequency potential, which is determines how rapidly a semiconductor device can turn on and turn off. So as you see here, the wide bandgap semiconductors, especially the gallium nitride, has the fastest switching frequency potential, which is around 1 megahertz, and this allows the materialization of power converters into the system weight. And here is the application mapping in EV systems. Here is a table of it. Now we consider the power electronics applications in the electric vehicles. And here is the background is that the performance and reliability and efficiency of a EV depends on the power electronic systems. And these power electronic systems depends on the wide bandgap semiconductors, which is silicon carbide and gallium nitride. And both of these wide bandgap semiconductors really affect the function of traction inverters, onboard chargers, and DC-DC converters. Let's start with traction inverter. So this component has a main function to convert DC from AC to DEF the electric motor. So the advantage of silicon carbide here is they have a wide bandgap, they have a high thermal conductivity, they have slow switching, they have fast switching speeds. And for the implementation of silicon carbide is that they can have a high efficiency, above 96%, improve thermal management, and extended driving range. Here is illustration of it. And we have the onboard chargers, which enables to charge the vehicle's battery using the alternating current from public charging stations. And we usually use the gallium nitride because it has high electromobility and high switching frequency capability, a low gate charge and output capacitance, a superior power density, and soft switching compatibility. And here we also have the example of companies who apply the gallium nitride on the OBC systems, which includes Toyota, Nvidia Semiconductor, and ZF Friedrichshafen. from Germany. So here is the illustration of the onboard chargers in the EV here. And we continue the DC-DC converters, which has a main function to step down high voltage DC to a low voltage. And usually the gallium nitride is applied to this converter because it has high power density, reduced size and weight by up to 70%, low ME emissions, high efficiency up to 98%, and it is particularly well suited for applications such as the resonant converter, supports multi-phase interleave converter, and ideal for smart power modules. And lastly, we have the implementation of DC converters in real life is by companies such as Valeo and Infineon that are developing for the power models. We have Neo and Xpeng Motors who have initiated a gallium nitride pilot programs. And here is an illustration of the DC-DC converter here in the EV. And here is the summary table of the application that we have just discussed. Next will be explained by my friend Kevin.
So, so my name is Kevin Pradipta, and today I'll present the performance analysis. So for the performance analysis, the implementation of WebG, SIC, and GAN is gonna improve notable improvements in performance in density, energy efficiency, thermal management, and system compactness. On the right side, we can see the material performance comparison, and the interpretation is the superior material like SIC and GAN enables higher voltage, faster switching speeds, and greater thermal resistance. Next, please. Performance analysis, ini power density and efficiency gains. So on the left side, we see switching loss reduction. So SIC exhibits to 80% lower switching losses compared to SI MOSFET. GaN high electron mobility transistor allow for extremely fast switching and reducing losses. For power density, SIC and GaN allows EV inverters and converters to be designed with higher density, and higher power density leads to smaller footprints, weight reduction, and battery utilization. And impact on EV efficiency, reduce switching and conduction losses directly. And smaller cooling system reduce vehicle weight, which further contributes to efficiency. Next, please. And the system integration benefits is higher frequency operation. GaN devices can switch at above 1 megahertz compared to silicon, which is less than 100 kilohertz. This enables miniaturization of passive components like inductors and capacitors. And on smaller magnetics and fewer cooling requirements result in lighter onboard DC converters, reduced housing cost and integration, greater flexibility in EV architecture and design, and reduce in electromagnetic interference. GaN clean switching characteristic leads to lower EMI. And on the real world impact, for instances, GaN based on OBC have shown 40% size reduction and 30% weight reduction. Next, please. So on the next slide will be explained by Audina.
My name is Audacia Bagustian, and I apologize. I cannot turn on my video. I don't know what happened to my laptop, so I'm going to explain about challenges in wide band gap adoption. So the first one is the next. The first one is cost per device and manufacturing maturity. It's about high device cost. Silicon carbide and gallium nitride devices cost much more than silicon. Silicon carbide MOSFETs can be 3 to 5 times the price of silicon IGBTs. High material cost due to complex wafer growth and lower production volumes limit cost reduction. Next. Manufacturing challenges, manufacturing and supply chain limitations. Silicon carbide wafers require high temperature sublimation growth. Gallium nitride grown on foreign substrates creates strain and defects. Limited foundries with high yield 6 to 8 inch wideband gap capacity. Specialized equipment raises capital cost. Next. The next one is reliability under long-term automotive stress. So here is the explanation about reliability under harsh conditions. Automotive systems face long lifetimes and extreme temperatures. Thermal cycling causes mechanical fatigue and delamination, and packaging often limits temperature capability more than the device. Next. Next is EMI and degradation mechanism. So here are the MEI and device aging challenges. Next. So here are the thermal management challenges. Next. So next is packaging and thermal interface complexities. So here is the advanced packaging requirements. Next. Last is standardization and regulatory issues. Here are the EMI safety and ecosystem issues regarding regulatory and integration challenges. Next.
And next, I'm Sylvia Najla Zahira, and I'm gonna explain industry outlook and trends. Next. So first is the power electronic industry is driven by the EV, of course, and adoption and sustainable goals. It's rapidly evolving to advanced semiconductor technologies such as silicon carbide and gallium nitride. This wide band gap semiconductor delivers significant benefits, including higher efficiency, thermal performance, and miniaturization, critical for modern automotive power system. Next. And the second one is the market drivers and policy support. So the global policies focus on reducing carbon emissions and energy independence are catalyzing investment in WBG technology in initiatives like the US Power American Program, the European IPCEI, and China 5-year plan enhance the research, production capacity, and standardization efforts necessary for industry growth. The major OEMs are rapidly expanding their EV portfolios, creating strong demand for power modules optimized for high voltage and fast switching. Next. The third one is the technology adoption and cost trends. So the CIC MOSFET prices are projected to decrease by 40 to 60% from 2024 to 2028 due to economies of scale and water size increases. And GaN devices are gaining and the GaN devices are gaining traction for compact high-frequency applications such as DC to DC converters and fast charging. Hybrid packaging combining SiC, and GaN component helps balance cost and performance across EV powertrains. Next. And the last one is the challenge and future outlook. So the challenges include higher initial costs, long-term reliability verification, and packaging innovation. However, advancement in water fabrication, collaboration between industry and academia, and emerging standards pave the way for wide-scale adoption. The power electronics market is expected to see transformative shift with WBG semiconductors becoming mainstream, driving efficiency improvements and enabling new vehicle architectures.
So I'm Kevin Varita, and I'm gonna explain the conclusion. So electric vehicles are growing fast and demanding smaller, lighter, and more efficient power electronics. Traditional silicon is reaching its limit, while new bandgap devices like SiC and GaN provides higher efficiency, better heat performance, and compact designs, perfect for our next generation's EV. Next, please. So silicon carbide has become the top choice for high voltage, high power EV system like tractions inverter and large onboard charger. Its wide bandgap lets it handle voltages above 12,000 volt. 1200 volt, perfect for long-range EVs and electric trucks. SEC also has higher thermal conductivity above 600 C, making it reliable in demanding automotive conditions. So SEC implementation in inverter system in Tesla Model 3 has up to 50% reduction in switching losses, improved motor efficiency, simplified thermal design, and lower system weight. Next, please. So GaN is ideal for high frequency, low to medium voltage applications such as DC to DC converter, auxiliary inverters, and faster charger. And it has up to 1 megahertz in switching capability and high electron mobility. And on the right side, we can see addition to power efficiency, GaN devices contributes to fast efficiency onboard charging, up to 6.6 kilowatt, smaller thermal footprints, reduce EMI, and enhance modularity and design flexibility. Next, please. So using SEJ and GaN in different parts of EV enables system-level optimization beyond silicon can deliver. This combination provides 40 to 70% of power losses. And on the right side, in addition to power efficiency, GaN-based devices contributes to extended vehicle range, faster charging time, lower total cost, and reduced battery size. Next, please. However, these challenges are rapidly being solved as each costs have dropped about 35% in the last 5 years, thanks to mass production, while GaN manufacturing is improving with innovation like GaN on silicon. Strong regulations and industry cooperations are also speeding up standardizations and adoption of wide bandgap technologies. Several challenges still hinder in WBG adaptation, wide bandgap, higher initial cost on SEC and GaN device mean more expensive than SE. Packaging and reliability, new packaging techniques are required to fully exploit the high temperature and high frequency, and then standardization, lack of universal accepted automotive standards for GaN and SEC. Next, please. So in conclusion, wide bandgap devices like SEC and GaN are the future of EV electronics, offering high efficiency, power, and sustainability as cost fall and adoption grows. The shift from silicon to ABG technology becomes inevitable and drive the next generation of electronic vehicle performance. Next, please. So that is all for us. Thank you so much for listening to our presentation, and thank you, Mr.